let us begin. Now, for acid-base equilibrium, right? What we're gonna be doing is adding a little bit of some bells and whistles onto our regular CSEC understanding of acids and bases, right? And where we're coming from is really the Bronsted-Lowry definition of acids and bases, or Arrhenius definition of acids and bases, and we're building on that. So prior to this topic in module 2, you would have looked at rates of reactions and you would have looked at chemical equilibrium, right? And the fact that reactions themselves don't actually go in a what do you say now, in a straight direction, right? But they can actually go in a dynamic movement back and forth, and these reactions, right, have the production of products and the reformation of reactants over and over again. Now, what happens in the case of acid and base reactions, right? Gonna have a look at that. Now, the theory of acids and bases that we're looking at here is the Bronsted-Lowry theory of acids and bases. And it has already been denoted that acids themselves, right, under this theory, right, are proton donors and bases are proton acceptors, right? So we just have to really, well, before we go any further, we really have to pick apart a simple equation, right, just to get this, to revitalize this information, right? So in this case, we're looking at hydrochloric acid reacting with ammonia, and that produces ammonium, all right? Ammonium ions, right, and chlorine ions. So we did state that acids, Bronsted-Lowry acids, right, can donate its protons, right? So in this case, right, the HCl would donate its proton to the ammonia, right? When it donates its proton to the ammonia, let's see that here, it donates this proton to ammonia, right? The ammonia now moves from NH3 to NH4, showing that it is increasing the amount of protons on the molecule, right, and gains positive charge there, right? So we know that there. So when the acid gives off its proton, right, it's going to be left as a chloride ion, right? So this chloride ion now is what we call the conjugate base, because now the chloride ion is open for the acceptance of a proton, right? So this is now called the conjugate base. So this is, oh, I could just write the arrow down there. It's a conjugate base, right? And when the ammonia accepts the proton that we looked at, right, and becomes ammonium, the ammonium ion is now what we refer to as a conjugate acid, because that ammonium now, the extra proton, can in solution release that proton, now donate a proton, right? So that's what's going to be happening. In the reverse reaction, we're going to actually have ammonium reacting with the chloride. So ammonium will act as an acid when it donates a proton back to the chloride, therefore it's a conjugate acid, and the chloride will actually accept a proton, right, from the ammonium to reform our acid. That's why it's called the conjugate base. It's basic in nature, it acts as a base, right? And we know our regular acid would be the hydrochloric acid, and our regular base would be our ammonia, right? So everything there should be fine. So if there are any questions or issues, just let me know, all right? So it's the same thing that is being displayed on here, right? So we have a carbonate ion reacting with water. In this case, water is the acid, right? We're reacting the water with the carbonate ion to give us a dihydrogen carbonate, right? And hydroxide ions, right? So in the reverse reaction, right, our conjugate acid, which is created in the forward reaction, right, can act as an acid, right, to donate the proton back to OH to reform water, right? So the base, when it accepts a proton, becomes a conjugate acid, right? And the acid, when it donates the proton, becomes the conjugate base. Make sense? Following, everyone? Lovely. All right. So, what are we looking at here now? In this theory, an acid is a substance that can release a proton. So we've been speaking about all of these different stuff, right? But in the Arrhenius theory, what we're talking about, right, it's similar to the Arrhenius theory. The Arrhenius theory speaks about increasing hydroxide ion concentration or increasing proton concentration, right? So if Bronson is saying that acids can donate protons, right, and Arrhenius is saying that we can increase proton concentration in solution, right? They're basically speaking about the same thing, right, with acids. With the bases now, Bronson-Lowry speaks to the fact that bases accept protons, right? But Arrhenius speaks to the fact that bases produce hydroxide ions in solution, right? So not every Arrhenius acid and base is a Lewis acid and is a Bronson-Lowry acid and base, and not every Bronson-Lowry acid and base is a Arrhenius acid and base, right? So there's different in that way. But let's have a look here, right? Looking at this reaction, we're looking at fluoride reacting with water to create hydrogen fluoride and hydroxide, right? We can clearly know, right, that we can clearly know what the acid and the base is here and what the conjugate acid and the conjugate base is here, right? When a Bronson acid, right, dissociates, it increases the concentration of hydrogen ions in solution, and conversely, when a Bronson base dissociates, it produces hydroxide ions in solution, right? So we're just banking on that information that we don't know before. All right. So a quick little exercise, right? If you could just pause here and just like write the information or take a screenshot, right, and just complete the information right here, right? I want you guys to be able to derive acid dissociation equations, base dissociation equations, and write the equations in relation to the acid dissociation constant and the base dissociation constant using different types of equations, right? Because if they give you a worded equation and you have to write out your chemical equation and then write out your acid base equation, right? Your acid dissociation constant equation, your base dissociation constant equation, you need to be able to do that, right? From stuff like this. So let's look at hydrogen fluoride reacting with the water to give us the hydrofluoric acid. Well, the fluoride reacting with water to do with hydrogen fluoride and hydroxide. Let's look at what's happening here, right? It generally takes this format for acids and bases. So acids generally dissociate to give you this anion, this conjugate base, which is the anion, right? And hydrogen ions in solution, right? Protons in solution, right? So we're gonna have something like this. This is our dissociation reaction. And how do we get the acid constant, the acid dissociation constant? You use Ka. So the acid dissociation constant Ka is given by the products divided by the reactants, right? So it's gonna be our concentration of our conjugate base, right? Concentration of our conjugate acid divided by, right? Or acid itself, the concentration of our acid. It's gonna be the same thing for the base. But with the base now, we know that we produce, right? Hydroxide ions, right? So it's gonna be our concentration of our conjugate acid and the concentration of our conjugate base, right? Well, concentration of our conjugate acid rather, and the concentration of the hydroxide ion concentration divided by the concentration of the base itself, right? So it's gonna be slightly different, right? So this is how it generally would look. So it's just products over reactants, right? Concentration of the products over the concentration of the reactants, right? And we tend not to include water, right? Because water itself will have a huge impact, right, on our acid or base dissociation constant. So when we're writing our Kas and our Kbs, we do not actually write water, include water in the reaction, right? Only the important ions. All right. Any issues there? Hopefully there are no issues there. All right. Lovely. So remember, if there are questions, you can always ask, right? Another thing that I want to go through specifically is what I define as P notation. So if we have a Ka and a pK, well, if we have a Ka and a Kb, right, we can derive what we call pKas and pKbs from it, right? So what P generally speaks to is a negative log of something, right? So if I were to give a definition for P, right, P would be equal to negative log base 10 of something, right? So if we talk about pH, what we're talking about is a negative log of our H ion concentrations, right? And if we talk about pKa, right, what we're talking about is a negative log, right, of our Ka, which is our products, concentration products, right, which would, this product would be here, over this, the negative log of this, right? Or what we could just denote as the negative log of pKa, right? That would be what pKa is, right? So P just means you're negative logging whatever value you have. So pH, negative log of the hydrogen ion concentration, pKa, negative log of Ka, pKb, the negative log of Kb, right? And in a situation in which you need to reverse this, you can anti-log, right? Or you can bring the power, right? You can bring the power of the negative pH in order to reverse something like that. We're going to be looking at that. You're going to have to use it in some type of questions, right? So in order to get something like a hydrogen ion concentration now, that's how you would do it, right? So in the case where you have hydrogen ion concentration and you negative log it to get the pH, right? How do you get hydrogen ion concentration from pH? Right? We can take 10 and bring it to the power of the negative pH value to get back your hydrogen ion concentration. Right? So that's another thing you can do. Right? So there are different mathematical tricks that we can use in this section in order to get our answers. Right? So bringing the 10 to the power of the negative value, that would be generally the same thing as a anti-log. Right? So I show you how to do the log, right? Negative log something, and how to reverse that P notation to get back your original value. Right? So let's have a look at this now. Right? So pH, as I was saying, right? pH, if we ask to define pH speaks to the negative logarithmic value of the hydrogen ion concentration. That is the definition for pH, the negative logarithmic value of the hydrogen ion concentration. And we know that pH speaks to acidity, basicity. We know that pH can be ranging from 0 to 14, with 7 being neutral, above 7 is alkaline, below 7 is acidic. We know that information. Right? This slide is just speaking about that, so you can stop here, right, and read it if you would like. All right? But if there are any questions or issues at this time, are there any issues? All right, not hearing any. All right, so looking at this now, right, this is just giving a synopsis of what we had here and the relationship that may be interesting to look at. So we know that pH is a negative log of the hydrogen ion concentration. We also have something called pOH, which is a negative log of the hydroxide ion concentration. And at 25 degrees Celsius, or what we call a standard temperature, pH plus pOH is gonna give us 14, right? So if our pH is 7, right, our pOH is gonna be 7. Well, if our pH is 7 rather, right, then we can find what our pOH would be. Because if pH plus pOH is equal to 14, right, if any of the values vary, we can figure out what the other value is using this relationship, right? So you can use relationships like these to check answers sometimes, but a good amount of times when you look at questions, they won't actually be the exact value that you're looking for, meaning that if they give you the Ka for like ethanoic acid, it may not be like the actual Ka, it might just be an arbitrary value in the question. So sometimes these types of stuff to check your answers may not be the best, right? But as long as you're working with numbers in the calculation, it should be fine. But at 25 degrees Celsius, pH plus pOH will give us 14. And it's a combination of that which gives us a maximum value on our pH scale, which is 14, right? It can also equal 0, depending on what you're looking at, all right? So this is basically what we're looking at for those calculations from pH, right? But for Ka, pK, Kb, and pKb now, right? As I was saying here, this information on the slide is just something that you could look at, or you could have a look at, right? But please remember that we're not using the addition of water. We're not using water in any of our equations because it doesn't really affect our equilibrium constant, right? So if you look at equations in which they have water, let me get my laser pointer. Right, if you look at the Ka is the acid dissociation constant, and what it does is it quantifies the extent to which an acid dissociates into its ions in a solution, right? And the pKb, is just the convenient logarithmic transformation of this constant obtained by taking its negative logarithm, right? So note on some past papers they may ask you what is Ka, what is pKa, what is pH, right? Notice I'm giving you all definitions, right? So that is important as well. So if we take the dissociation of for like an acid, right? We have water here. We just need to remember that water is not included in any of the equations, right? And if we look here, right, notice that water is not included. So if you have an acid like here reacting with water to give us something, do not include water, right? As well, you might see the inclusion of a hydronium ion, right? So our H3O plus, right? That concentration is similar, is the same thing as the hydrogen ion concentration. So you can use them interchangeably. I personally tend to use hydronium ion concentration more because I feel it's somewhat more correct, but it's fine. You can use any of them in any of the symbols interchangeably. They would be the same. All right. And it kind of really depends on the solvent, but I don't think we go that in depth, right? In unit 1. But that's what's having here, right? So we have the Ka being that relationship there, and our pKa would be the negative log of the Ka that we have up there, right? And we can say that pH, right, is equal to the pKa, which is equal to the negative log of the Ka at half the equivalence point, right? And that would be what you have looking at something like a titration. Well, not really a titration, but when you're looking at acid-base equations or acid-base reactions, at half the equivalence point, we're gonna have pH being equal to pKa, which is equal to negative log of the Ka. All right, but we don't really use that relationship a lot. We just normally focus on Ka and pKa. All right. And here are some questions that you guys can try, but I'm not gonna actually go through the questions right now. But you can take a picture, take a screenshot or something, right, and try the questions, and you can send me the answers, and we'll have a discussion as to like what is the proper treatment of the question and whether or not your answer is correct. Okay? Is everyone doing so fine so far? All right. Hopefully everyone is doing well. I can also see the chat and everything, so if you don't want to like unmute your mic, you can type a question in chat if you want, and I'll answer it. Okay. All right. So KB and pKb now, I think it's kind of painful repeating the same thing over and over again, because it's really the same thing again, right? It's gonna be right or the same KB equation, which is just the same thing as Ka but for bases, and then we're gonna have the pKb, which is the negative log of the Kb. All right. Now it is important to really note the similarities, or well, not the similarities, but the relationships between the two. Right. Here are some other questions as well that you could try and send me the answers for us to look at. Right, but we have to understand the relationship between the Ka and the pKa and the Kb and the pKb. So if we look at the relationships between the Ka and the pKa, right, we could look at the fact that the acid strength itself is a fundamental concept in chemistry. That's what it's saying there, right? It's really, really fundamental. So it really speaks to how much protons are dissociated in solution, right? The stronger the acid, the more ions it can produce in solution, right? The more protons, right, it can produce, right? So that's what's happening with the Ka, right? The acid dissociation constant quantifies the extent of dissociation, right? So it quantifies how much an acid releases its protons. So the more an acid releases its protons, the stronger the acid, right? So we have to understand that. So this equation elucidates that the higher Ka value signifies a stronger acid, right? Why is that so, right? Because a larger Ka indicates a higher concentration of our products. Because in order to get a higher Ka, our products must be larger than our reactants, right? Meaning that the acid must be producing more hydrogen ions than the concentration of the acid itself. So that would mean that if the Ka is larger, the acid strength is larger, or the acid is stronger, right? So really what we're talking about is that the Ka is directly proportional to the acidity, right? So the larger the Ka, the stronger the acid, right? So you can note that. Hopefully everybody gets that, right? But for pKa, now that we're taking the negative logarithm of this value now, right? The pKa actually is inversely proportional to acidity, right? So what we're saying is that the higher the pKa, the lower the acidity of our acid, right? So that's the relationship. So the higher pKa indicates a weaker acid, right? That's something that we need to remember, especially for unit 2. We need to remember this information, right? Is everybody following so far? Hopefully we're all following. Hopefully everything is fine. All right. So the relationship between the pKb and the Kb is the same thing, right? So this topic isn't really that bad, right? So it's really the same thing. We're repeating things over and over again. So the Kb, you know, is directly proportional to basicity. I'm gonna wonder how to basicity. Basicity is a weird word, right? But it's directly proportional to the strength of the base, right? And pKb now would be inversely proportional to the base strength, right? So that's what we're having here, inversely proportional. Lovely, right? So just keep that in mind. Ka is directly proportional to acidity. Kb is directly proportional to basicity, right? pKa is inversely proportional to acidity, and pKb is inversely proportional to basicity, right? The higher the Ka, the stronger the acid. The higher the pKa, the weaker the acid. The higher the Kb, the stronger the base. The higher the pKb, the weaker the base, right? So when you get into relational problems like this, the higher the pKb, the stronger the acid, right? Meaning that strong acids have really high pKbs, right? But you would have a high pKb value, right? Well, because it's not basic at all, really, right? So we could look at all of those type of stuff, right? So it's just a relationship between the two, right? Now, that's really all we need to really do the calculations that I proposed before, right? But let's have a look at this. Acid-base titrations, right? We know what titrations are. Titrations are these types of methods that we use to find the concentration of an analyte using a titrant, right? To really find that, right? So we set up a burette, right, that dispense some volumes of an acid or a base into a solution, right? In order to find that concentration, right, through mole ratios when the reaction ends, right, when there's a complete neutralization, right? And how we know that when that reaction ends, when we have an indicator. We should remember that, right? So let's have a look at that, right? How does pH change, right, in relation to adding a strong base or adding a strong acid, right? We know that the stronger the acid, the closer the value is to 0, and the stronger the base, the closer that value is to 14. So in the case of a strong acid being added to water, because water would be at 7, you can see at 7 here, the more acid you have, there's gonna be a huge drop and then a curve here that flattens out, reaches a plateau, right? So the acid, the HCl is gonna drop close to 1 as we continue to add volumes of HCl. And if we have NOH now, right, if we add sodium hydroxide to water specifically, the pH is gonna boost straight up and get closer and closer to 13 there, right? So it is important to know how graphs look, right? pH graphs look, right? Titration graphs especially look, right? We have to look at the pH of the solution in relation to the volume of acid or base being added to the solution, right? In this case, it's just water, so you're just showing what would happen in this case. But what happens if you have a strong acid being titrated again with a strong base, right? Titrated with means that there's a strong acid existing, and then we start to add base to it. So the strong acid itself will have a pH below 2 here, we'll around 1 here, right? And then as we add a base, right, it's going to go up, right? And then we have something that we call an equivalence point when the pH really buffers out, or the pH really singles out, like a buffer system is created here. And we're gonna talk about buffers later, right? But it kind of like becomes one vertical line with a kind of that shoot up, right? The buffering area is actually around here or around here, where pH doesn't really change that much anymore, right? But here now is a critical point within a titration where the pH changes drastically, right? In the middle here, right, at around 7 is our equivalence point, right? So at half the equivalence point, right, we stated our relationship before, right? Wondering if you guys can let me know what that is, right, in the chat. But we said the relationship before. It's not really that important, but it's in the PowerPoint, right? So we have adding a strong acid to a strong, adding a strong base rather to a strong acid.
Sorry, confirm what you state in the chat.
On the chat, we had a relationship before, right, between pH and a pKa, right? What happens, right, when we're at half the equivalence point, right? The pH of the solution would be equal to the pKa, right? So I was just mentioning that, right? I don't think it's something that we tend to use a lot, but it's a relationship that has been observed, okay? So when we're adding a strong base to a strong acid, right, it's going to move from a very low pH into a very high pH. When we're adding a strong acid now to a strong base, the strong base is going to start out really basic, and then we're going to have some amount of slow change. So there's not going to be any drastic changes in pH, and there's going to be a quick change down into the acidic region. All right, so we have like small buffering regions where pH doesn't really change that much, and then you have a sharp change here, right, when the buffer has reached its capacity, when it's broken, right? And we'll talk about buffers in the buffer section, right? So this is what's happening with strong acid and strong bases, right? What happens with a weak acid being titrated with a strong base? A weak acid now, the only difference is that the weak acid will start out a little higher. That's the only difference. It starts out a little higher than the strong acid, because a weak acid would have a pH that is closer to 7. So that would make sense. Same thing for the base. The weak base would have a pH closer to 7. Right? So you can see how the curve is much closer there. Right? So it's much shorter than what you would expect for strong acid, strong base, right? Or strong strong acid, strong base reactions, right? So that is what's happening there. So hopefully it just makes a lot of sense. Hopefully you just see it and it just makes sense. All right? Not sure if there are any questions. If there are any questions, please ask. All right. So for weak acids titrated with strong bases and weak bases titrated with strong acids, right? We can see this here, right? pKa and pKb, right, at different midpoints. We can see how those arise, right? Through the graphs, right? So around the neutral region, the pKa is 7, right? And the pKb is 7 around the neutral region for bases when we're adding acids and bases, right? When we're adding an acid, the pKa can be around 4 here, because the higher the pKa, the weaker the acid, right? So the pKa is increasing, and notice that, right? Of the solution, the stronger the acid, right, the lower the pKa, right? So the pKa may be really small here, and notice as pH changes, the pKa increases, right? And for when we're adding an acid now to a base now, right, the pKb starts out really low, because remember, lower the pKb, the stronger the base. So as the base breaks and becomes more acidic, the pKb increases. So notice the inverse proportionalities and the inverse relationship between pKa and acidity and pKb and basicity. All right, we need to know that. We need to remember that. Okay. All right. For indicators, however, now, right, we would remember what indicators are. Indicators are components that give some amount of color when pH changes in a specific region for them, right? And this is how we know when to stop a titration. This is how we know the end point of a titration. And it's important to also know that endpoints and equivalence points are two different things. Endpoints are points that we can see that are close to the equivalence point, but it's rare. It's the probability is close to zero that a human can actually get exactly the equivalent point for titration. It's really, really rare. It's probably close to impossible, right? But we can get endpoints, and then we can use that, right, those values as if it were equivalence points to really find the concentration of an analyte, right? So indicators now. The pH range of indicators are really important. We know that pH indicators have specific pH ranges, which changes color, right? Which have a change in color, right? The pH range of an indicator should overlap with the pH range expected during the titration to ensure accurate endpoint detection, right? So this is really coming into a part of the syllabus where it asks us to be able to identify the best indicator, right, for acid-base titration, right? So I have a plethora of different types of indicators here. So let's have a look. Choosing the right indicator. The choice of indicator depends on the type of titration being conducted and the pH at the equivalence point, right? The titrations involving strong acids and strong bases, right? For those titrations, indicators with pH ranges around the equivalence point of 7, right? pH 7 is suitable. For example, our methyl orange and our bromothermal blue, right? In titrations where we have weak acids with strong bases or vice versa, strong bases with weak acids, right? Indicators with pH ranges that encompass the equivalence point of the specific reaction is preferred, right? For instance, phenolphthalein is really suitable for titrations involving weak acids and strong bases due to its color change occurring in the pH range close to the equivalence point of a weak acid strong base reaction. So if we look at weak acid strong base, right? Weak acid strong base, right? The equivalence point for the weak acid strong base is somewhat within this lower region, right? So phenolphthalein really operates in that region, all right? Wait, it says weak acid strong base. Yeah. All right. So it's based on where your equivalence point is really. It's crucial to select an indicator whose pH includes the expected pH at the equivalence point of the titration. This ensures that the color change occurs precisely when the reaction is complete, right? So looking at strong acid, strong base titrations, we have methyl orange, which would be good, and phenolphthalein, which is good as well, right? Phenolphthalein changes from color as pink, right? And methyl orange changes from red to yellow. For strong acid weak base titrations now, right? Methyl orange is really good, methyl red is really good, and bromothermal blue is really good, right? For strong base weak acid titrations, phenolphthalein is good as well, methyl orange is good, and bromothermal blue is also well, right? So notice that phenolphthalein and methyl orange tends to be the indicators that are more common, right? But they're really, really common and they cover a wide range. For more specific, more accurate titrations, we tend to use pH indicators with a smaller range, right, in order to get the most accurate as possible endpoint, right? For weak acid, weak base titrations, we can also use these. All right, bromothermal blue would probably, but it depends on where we're going, which direction, right? Because if we're gonna be adding acid, then we could probably be using the methyl orange and the methyl red. If we're gonna be adding base, we can use the phenolphthalein and the bromothermal blue. But remember, it always speaks to the change region, right? Change in pH that region there on the graph, as well as the equivalence point. All right. So we have this here, right? So the different acid colors and base colors and the pH ranges of our different indicators. Are there any questions or concerns from me so far? So hopefully this is all fine.
No, sir.
Lovely. Right, so this is also a question that I would like you guys to have a try with, right? It's a situational question, right? You have 3 bullet points of information and you need to give us the initial concentration of the weak acid, right? The concentration of the conjugate base, the concentration of the weak acid, all of at the equivalence point, as well as give us the pKb value of the conjugate base, right? But the question is there, see if you can find the answer, all right? So that would be it for acids and bases. Right, acid-base equilibria itself. right? Because this is the information that we use, right? But of course, the questions we need to practice the questions with this information, and we will be fine with that. We should be fine with that, right? That's it.